A single silent ember flickers at the edge of time. James Webb Space Telescope catches it not in a blaze but in a patterned darkness, in the bluest light a sudden rise in the red. Astronomers call it MOM-Z14, a compact galaxy, born only a few 100 million years after the beginning of cosmic expansion. No arcs, no mirrored ghosts, no noisy tricks, just a clean break and a steady glow from young stars. In the next minutes, the journey moves from that faint pixel to a measured frontier distance structure, dust gas and the cautious tests that turn a whisper from dawn into a record. The light from MOM-Z14 first appears as a small, faint and distinctly red patch. In deep near-infrared images, an island of flux that rises above a very quiet background when the data are stacked and cleaned. The field is crowded with dim sources, yet this one stands out because it is not seen in the shorter wavelength frames that reach similar depths, while it remains consistently present in the longer wavelength frames, taken at the same sky position and under the same observing pattern. The identification begins in the image plane with a straightforward rule set that has been used in many deep surveys: require a non-detection at shorter wavelengths, at a well-defined upper limit require significant detections in at least 2 redder bands, and require that the centroids of those red detections agree within a small fraction of a detector pixel after astrometric alignment. MOM-Z14 satisfies these tests. At wavelengths below, roughly 1 1/2 micrometers, the images show no statistically significant flux at the candidate position when measured in apertures matched to the local point spread function and corrected for aperture losses. At wavelengths around 2 micrometers and longer, a compact source is measured with high signal-to-noise, and its position is consistent across all the redder bands as well as across independent reductions. The data are taken in multiple dithers that shift the field by small steps, so that bad pixels, cosmic rays and other detector defects land on different places relative to the source. The stacking process rejects those outliers and preserves real sky signals. MOM-Z14 remains at the same celestial coordinates in every dither and exposure where the band coverage supports a detection, which argues that it is not a transient artifact tied to a single frame or a single readout channel. Persistence from a saturated source is a known risk in near-infrared detectors, so the frames immediately preceding the exposures are checked for bright sources at the same detector position. None are found within the persistence risk window. Diffraction spikes from bright stars can masquerade as faint linear structures, but the source lies far from any spike pattern and appears compact rather than elongated along a spike direction. Ghost reflections and scattered light features are mapped by comparing the field to calibration templates, and the position of MOM-Z14 does not coincide with a known ghost locus. Automated source finding uses a detection image formed by combining the longer wavelength bands with inverse variance weights, and then measures fluxes in each individual band at the positions of the segments found in the detection image. MOM-Z14 is detected as a single compact segment with no obvious substructure, and its measured half-light radius is only slightly larger than the radius expected for an unresolved object at these wavelengths. The photometry is performed with both fixed circular apertures and small apertures scaled to the local point spread function, and the results agree after standard aperture corrections are applied. The sky background is estimated in annuli around the source, and as a check in local background windows free of visible sources. The measured flux varies within the statistical uncertainties expected from the noise model. To test the robustness of the detection, the dataset is divided into 2 halves, separated in time, and separate stacks are made for each half. MOM-Z14 is present in both halves, with comparable flux and shape, and its centroid remains stable. A parallel test splits the data by detector position, so that the source falls on different regions of the array. Again, the signal persists with consistent properties. The same measurements are repeated with slightly different background subtraction parameters and with mild changes to the way the images are registered before stacking. The presence and brightness of the source change only within the range predicted by the propagated uncertainties. The selection relies on color cuts that are designed to isolate sources whose light is sharply suppressed at shorter wavelengths and rises at longer wavelengths. These cuts are phrased in terms of measured fluxes and their uncertainties rather than in terms of model assumptions. The flux in the bluest near-infrared band is required to be below a 2 standard deviation upper limit, while the fluxes in at least 2 redder bands must exceed a 5 standard deviation detection threshold. The colors implied by these measurements place MOM-Z14 in a region of color space that is sparsely populated by known low-distance galaxies and by cool stars when those objects are observed at comparable depths. To check for contamination by very cool stars that can appear red, the shape of the source is compared to the point spread function, measured from nearby unsaturated stars. MOM-Z14 appears marginally broader than the point spread function, although the difference is close to the resolution limit, so the test does not on its own exclude a point source. The color combination carries most of the discriminating power. To check for contamination by dusty low-distance galaxies whose spectral energy distributions can mimic a red color, the photometry is compared against a library of such galaxies embedded in noise at the same depth. Those interlopers tend to show measurable flux at least in one of the shorter wavelength bands, or they present colors among the red bands that differ from the set measured for MOM-Z14. In the present case, the source remains non-detected at shorter wavelength to a tight limit, and shows internally consistent fluxes among the red bands that are well reproduced by a sharp break followed by a smooth rise. Neighboring sources can bias the photometry of a faint object, so the segmentation map is examined for blending and the deblending parameters are varied. The measured fluxes for MOM-Z14 remain stable within the noise when these choices are changed, which indicates that the object is sufficiently isolated for reliable photometry. A forced photometry test measures the flux at the candidate position in all bands, including those with non-detections, to ensure that negative boles or residual background structures are not driving the non-detection. The flux in the bluest bands remains consistent with 0 within the expected noise. Finally, simulated sources that match the observed size and brightness are injected into the real images at random positions, and the full detection and measurement procedure is repeated. The recovery rate and the recovered colors show that an object with the properties of MOM-Z14 would be found with high completeness under the same conditions, and that interlopers with ordinary colors would be rejected at high purity. The conclusion at this stage is limited to image plane facts. A compact source is consistently detected at longer wavelengths. Its position is stable across exposures and reductions. It remains absent at shorter wavelengths to stringent limits, and known classes of image artifacts are disfavored by direct checks. These criteria are exactly the ones that motivate its selection as an extreme distance candidate, and they form the outer layer of evidence on which all later inferences are built. The distance to MOM-Z14 is inferred from how its light distributes with wavelength and whether light fades from view. In deep imaging, the source is absent in the shorter near-infrared bands, while present in the longer near-infrared bands a pattern that points to a pronounced discontinuity in the spectrum. The most natural explanation for such a discontinuity at these wavelengths is the hydrogen Lyman-alpha break, which at a rest wavelength near 121 nanometers is shifted by cosmic expansion far into the near-infrared for sources in the early universe. If the flux suppression is caused by the intergalactic medium absorbing light blueward of this transition, then the position of the break across the filter set provides a first estimate of cosmic epoch. This estimate begins with measured fluxes and limits, not with a model spectrum. Photometry in each band is compared to the instrument throughput curves, so that the effective wavelengths are clear and upper limits. In the bluest bands are treated consistently as constraints on allowed solutions. Template fitting is then performed with a wide library of spectral energy distributions that include young stellar populations with nebular emission, older stellar populations with more developed breaks, and dusty low-distance galaxies. For each template, a redshift is scanned, and synthetic fluxes are computed through the same filters, and the likelihood that the template at that redshift matches the observed fluxes and limits is recorded. The result is a probability distribution over redshift. When the best-fitting solutions align the hydrogen break between the bands that bracket the transition from non-detection to detection, the probability accumulates at very high redshift, while low-distance solutions generally require fine-tuned dust, reddening, and strong emission lines to hide flux in the bluest bands and replicate the red colors in the redder bands. The analysis also checks for a Balmer or 400 nanometer break at modest distances that can mimic a red color. In that case, the source should retain some measurable flux in at least one of the shorter, near-infrared bands, or it should display a different pattern among the redder bands than what is observed. The measured colors of MOM-Z14 show a sharp step rather than a gradual curvature, which favors a Lyman-alpha interpretation under simple assumptions. A preliminary low-resolution spectrum, when available from a slitless grism or a prism mode, can add an independent view. If the spectrum confirms a strong discontinuity at a wavelength that aligns with the photometric break, it supports the high redshift solution, even if no discrete emission line is detected. The spectral extraction is carefully checked for contamination from overlapping traces, and the background fit is varied within reasonable bounds to test the stability of the break position. In the absence of a clear emission line, the center of the break carries an uncertainty that reflects the finite resolution, the noise, and the shape of the intrinsic continuum just redward of the break. The inferred epoch depends not only on the break position, but also on how completely the intergalactic medium absorbs the blue side. At very early times, the neutral fraction of hydrogen is high, so the absorption is strong and the break is deep, but the exact depth can change with sightline and with local ionization conditions. The fitting process, therefore, allows the blue side to vary within physically reasonable limits, rather than fixing it to a single value. Photometric calibration and filter curves are another source of uncertainty that enters the redshift probability. Small shifts in the effective wavelengths or small offsets in 0 points can move the favored redshift by a fraction that is significant when the filters are wide. To capture this, the analysis perturbs the calibration within its stated uncertainties and recomputes the probability distribution, then folds that spread into the final bounds. The presence of strong nebular emission lines redward of the break can also bias the estimate by adding flux to a band and changing a color. The templates include such lines tied to the star formation rate and metallicity, so that the algorithm can reproduce very red colors without invoking extreme break positions. In practice, these solutions tend to predict detectable flux blueward of the break, or inconsistent colors in adjacent red bands, and the data for MOM-Z14 do not display those patterns within their limits. A consistency check compares solutions derived from independent reductions of the same images and, when possible, from different pipelines that treat background subtraction and aperture corrections slightly differently. The favoured redshift peak persists and retains similar width across these tests. A further check reweights the templates to avoid giving undue emphasis to any single class of galaxies. The redshift solution for MOM-Z14 remains dominated by break placement, rather than by detailed continuum shape, which is appropriate at such faint levels. The final outcome of this step is not a single number, but a range with a central value and credible intervals. The central value lies in the regime associated with the first few 100 million years after the beginning of cosmic expansion, and the interval width reflects the combined effects of measurement noise calibration, uncertainties template diversity, and the partial degeneracy with dusty interlopers. The role of the preliminary spectrum is to tighten the interval by anchoring the break more precisely. When the spectrum is absent or too noisy, the interval is correspondingly broader. Throughout the method keeps the inference close to observables where the source is seen where it is not seen, and how the transition aligns with well-understood atomic physics. The distance estimate at this stage is therefore robust to the degree that the break is real and centered between known filters and limited by the bandwidth of those filters, the noise in the images and the residual possibility that an unusual low-distance object with heavy dust and extreme lines could mimic the colors. These caveats are recorded explicitly so that later sections can carry them forward as bounds on all derived quantities that depend on the cosmic epoch. The immediate neighborhood of MOM-Z14 is examined in the image plane so that context is set only by what the pictures record. The inspected field spans many tens of arcseconds on each side, large enough to include companions that might bias measurements, and wide enough to reveal whether faint structures trace early clustering. The processed background appears uniform with residual gradients below the statistical noise on aperture scales used for photometry, and the scatter of empty sky apertures matches the noise model. Difference images between temporal subsets show no pattern tied to a single exposure, and no residual striping or banding appears at the candidate position. Bright foreground stars concede diffraction spikes, halos, and internal reflections. A map of bright stars within a radius of a few arc-minutes shows none whose spike geometry crosses the source at significant intensity, and the nearest saturated star lies well outside the radius, where its halo would matter at this depth. The instrument orientation places the known spike directions far from the target. The local background lacks alternating motifs, and the candidate appears compact and round rather than elongated along a preferred angle. To assess possible clustering, a conservative color selection is applied to all sources detected in the red bands. Objects undetected in the bluest near-infrared band to a tight upper limit, and detected with high significance in at least 2 redder bands are flagged as red neighbors. Their angular positions relative to MOM-Z14 are measured, and their surface density within a small radius is compared with the average across the field. The count within several arcseconds is modestly elevated but remains consistent with chance, once small number uncertainties are considered, and a 2-dimensional map shows no clear filament converging on the candidate. These tests suggest that if clustering exists on these angular scales, it is weak at the present depth. Contamination of the photometry by nearby sources is tested in the images. Segmentation maps indicate that the footprint of MOM-Z14 is separated from adjacent footprints by a buffer of sky for a reasonable range of deblending parameters. Photometry repeated with slightly larger and slightly smaller circular apertures returns fluxes that vary by amounts consistent with the propagated noise, and aperture corrections based on isolated stars reproduce consistent totals. A model of the local point spread function, fitted to the profile leaves, small symmetric residuals, and subtraction of the fitted model does not reveal hidden substructure from an overlapping neighbour. A forced subtraction of light from the nearest object using its measured profile at a mirrored position changes the flux of the candidate by much less than one standard deviation. Motion is another risk, since a slow, moving body in the outer solar system can appear as a faint point if a stack covers too short a baseline. The individual exposures are separated by many minutes and are taken with a dither pattern that shifts the sky by small steps, so a moving body would produce a short trail or a centroid that drifts between frames. The source remains stationary within the astrometric precision. Its shape does not broaden along a consistent direction, which disfavours a moving or transient origin. The field is examined for diffuse patterns that might be misread as groups of companions. After smoothing the red detection image with a gentle kernel, wide enough to suppress isolated points while preserving broader features, no arcs, bands, or patches appear near the candidate. The sky shows no sign of galactic cirrus at this depth, and there is no large-scale gradient correlated with telescope orientation. The background measured in annuli around the source matches the distribution from randomly placed sky windows, which indicates that the local environment is typical of the field. Foreground galaxies at lower distance are catalogued to test for overlap with the line of sight. Several galaxies within a few arc-seconds show clear detections in the bluest near-infrared band, and in shorter wavelength images marking them as foreground. None overlaps the aperture of MOM-Z14, and none exhibits an extended halo bright enough to intrude into the photometry. The nearest of these galaxies shows a smooth profile without tidal features, and the distance between its isophotes and the candidate exceeds the aperture radius used for measurement. Consistency across independent reductions strengthens the environmental checks. Two pipelines that differ in background modelling cosmic ray rejection and image registration recover the same set of red neighbours and measure similar fluxes for the candidate within their respective error budgets. A jackknife split by detector region, which forces the source to land on different parts of the array, yields consistent photometry and morphology, indicating that local detector features are not driving the detection. The immediate environment is therefore quiet in the sense required for reliable interpretation. There is no bright star structure at the position, no moving object signature, no stray light pattern, and no overlapping foreground halo that would bias the measurement. A handful of faint red neighbours share similar colour behaviour within a small radius, but their number is small and their distribution is not strongly concentrated. The environmental facts at this stage remain strictly local and descriptive. The sky around MOM-Z14 is typical of the broader field the candidate is isolated for photometry, and any hint of clustering is weak and not decisive at the present depth. The compact morphology of MOM-Z14 is measured in the longest wavelength images, where the signal is strongest using models that describe how light is distributed on the sky after the instrument has blurred it by the point spread function. The first measurement is a non-parametric half-light radius, defined as the circular radius that encloses half of the total light within a large aperture after standard aperture corrections. The value is marginally larger than the radius measured for isolated stars in the same image, which indicates that the source is slightly extended but close to the resolution limit. A curve of growth built from concentric apertures increases smoothly with radius and approaches a stable total at a radius of a few times the stellar half-light radius, with no secondary shoulder that would suggest a broad halo or a distinct outer component. The surface brightness profile is then modelled with simple forms that are widely used in galaxy studies, A single Cirsic profile convolved with the local point spread function provides an adequate description, and the best-fitting Cirsic index falls near unity, within substantial uncertainty, consistent with a shallow central concentration. A de Vaucouleurs like concentration with index near 4 is disfavored because it predicts a stronger central cusp and a slower fall-off than the data allow at this depth. Residual images obtained by subtracting the best-fitting convolved model show small symmetric structures consistent with the remaining mismatch between the real point spread function and the empirical model rather than with true substructure. Elliptical isophote fits recover an axis ratio close to unity with large error bars as expected for a barely resolved source, and the position angle is poorly defined, which again argues that any observed elongation is at most mild. Tests that adjust the drizzle kernel, the pixel scale and the weighting of the individual exposures change the measured radius and concentration by amounts comparable to the propagated uncertainties, not by dramatic factors. The effective radius derived from the model fit agrees with the half-light radius from the non-parametric measurement within one standard deviation, which strengthens the case that the size estimate is not an artifact of a particular method. To guard against biases from correlated noise introduced by image combination, the noise covariance is estimated from empty sky stacks processed through the same pipeline, and the uncertainties on the profile are inflated by that covariance. The inferred size and concentration remain within the same bounds after this correction. A two-component fit that allows a compact core plus a faint extended envelope is attempted as a stress test. The envelope component is not required by the data at the present depth. When included, it tends to absorb small mismatches between the empirical point spread function and the true blurring kernel rather than revealing a genuine low surface brightness wing. A forced two-component model yields an envelope with a scale length that is consistent with 0 within errors, and the core retains most of the flux. This outcome suggests that if a very faint extension exists, it lies below the current surface brightness limit set by the exposure time in the background. The morphological measurements are repeated in a second red band, where the source is still detected with high significance, but where the resolution and sensitivity differ. The apparent size changes by less than 1 standard deviation, and the concentration parameter shifts by an amount consistent with the change in signal to noise. The agreement across bands implies that color gradients, if present, are not strong enough to alter the overall shape at the current depth. Neighbor subtraction tests address the risk that a faint companion blended within the seeing disk could mimic a broader profile. Profiles of nearby sources are mirrored and subtracted around the candidate, and a simultaneous multi-object fit is performed, where the shapes and positions of adjacent objects are fixed by their own measurements. The recovered size of MOM-Z14 remains stable across these tests, and no coherent residual appears at an offset position that would signal a blended companion. A stack of the residual images rotated by random angles and centered on the source yields a pattern consistent with random noise, which supports the conclusion that there is no hidden asymmetric tail or arm. The analysis also examines potential morphological bias from charge diffusion and detector intrapixel response. Stars across the field exhibit a small variation in measured size with subpixel centroid, but this variation is absorbed into the empirical point spread function model, constructed from many stars. Applying that model at the position of the candidate removes the trend. The remaining difference between the source size and the stellar size is therefore attributed to the source itself rather than to detector behavior. Because the object is only slightly resolved, the translation from angular size to physical size depends on the distance estimate and carries the same fractional uncertainty. the present section does not convert to a physical scale. It records the angular constraints alone. Within those constraints, MOM-Z14 is compact with light that is centrally concentrated but not sharply cusped, and with no secure detection of a diffuse outer component. The mild extension above the point spread function argues against a pure point source such as a cool star, yet the proximity to the resolution limit leaves room for future refinement, with deeper images or higher resolution measurements. All derived morphology quantities are reported with errors that include measurement noise, background covariance uncertainties in the point spread function model, and the spread across independent reductions. The image plane facts are consistent across tests: a small, nearly round and slightly resolved source, whose surface brightness declines smoothly without pronounced features, whose size is robust to method choices, and whose shape shows no verified asymmetry at the present depth. These facts complete the compact morphology view required before advancing inward to the distribution of energy with wavelength. The distribution of energy with wavelength for MOM-Z14 is assembled from measured fluxes and firm upper limits across the available filters with care to assign each point to the correct effective wavelength once the instrument transmission and detector sensitivity are folded in. The defining pattern is a pronounced step no statistically significant flux in the bluest near-infrared band and a sequence of secure detections in 2 or more redder bands. That step sits where the hydrogen Lyman-alpha transition, which in the rest frame lies near 121 nanometers, would be shifted by cosmic expansion into the observed near-infrared for a source in the first few 100 million years after the beginning of expansion. The photometry redward of the step rises gently with wavelength consistent with a relatively blue continuum once the effect of intergalactic absorption on the blue side is acknowledged. To visualize the evidence, the measured fluxes are converted to average specific flux densities within each band and placed at the filter pivot wavelengths, while non-detections are treated as 2 standard deviation upper limits. The bluest band contributes only an upper limit that sits well below any smooth extrapolation of the red points, and the first red detection appears at a wavelength that brackets the expected position of the break. A second and often third red detection confirm a coherent upward trend rather than a single outlying measurement in a low-resolution spectrum, where available shows a downturn at a comparable wavelength within the limits set by the disperser and extraction. Because broadband filters integrate over wide wavelength intervals, the exact placement of the break is inferred statistically by scanning trial break positions and fitting a power law continuum on the red side with 0 blue flux. The fit quality peaks when the break falls between the bands that divide non-detection from detection and declines on either side as the model predicts too much blue flux or too little red flux. Introducing a flexible continuum slope described by a power law index, often called beta, yields a negative value with moderate uncertainty, which indicates a continuum that becomes fainter toward shorter wavelengths and is compatible with young, moderately unobscured stars under simple assumptions. At the present depth, beta remains sensitive to small calibration offsets and to possible emission line contributions that add light in one band more than in its neighbours. To bound such effects, synthetic spectra that include nebular emission across a range of ionization states and metallicities are passed through the same filters. Solutions with very strong lines can reproduce red colours without a high break, but they often predict detectable blue flux or inconsistent red band ratios that are not observed. The observed red band fluxes of MOM-Z14, when compared pairwise, follow the monotonic sequence expected from a smooth continuum rather than the jagged pattern that discrete strong lines would create. Another possible mimic is a dusty low-distance galaxy, reddened by absorption, and scattering by dust grains. Dust reddening produces gradual curvature across bands rather than an abrupt step, unless an unusually strong 400 nanometer break is present. Templates with such breaks usually leave some residual flux in the bluest near-infrared band at the present depths, or require finely tuned dust and line strengths outside the ranges measured for similar systems. The colours of MOM-Z14 do not show gradual curvature. They show a step followed by a mild slope, which more naturally aligns with a high redshift break. In independent reductions, adjacent red band fluxes track one another within their uncertainties as expected, for a continuum source, rather than a spurious feature confined to one band. Forced photometry in the blue band returns values consistent with 0 within the noise model, and small changes in background annuli or aperture sizes do not tip the measurement into significance. A check for correlated errors measures the covariance between band fluxes in empty apertures. The covariances are small compared with the difference between blue and red measurements, so the step is not an artifact of shared noise. Where the low-resolution spectrum is present, contamination from overlapping traces is modelled and subtracted, using positions and profiles from the imaging and the residual continuum. Near the break remains consistent with a real discontinuity, though broadened by finite resolution. Photometric zero points and filter curves introduce additional systematics. To propagate them, the analysis perturbs the 0 points and effective wavelengths within their calibration tolerances and recomputes the continuum slope and break position. The outcomes widen the error bars but do not remove the preference for a high break. The resulting spectral energy distribution is deliberately simple and observational, strong suppression of flux blue ward of a well-constrained wavelength interval, a smooth and moderately blue continuum redward of that interval, and no compelling evidence for discrete features within current sensitivity. This description anchors the identification of MOM-Z14 as a very distant candidate, without appeal to detailed population synthesis, and prepares later steps that translate continuum level into star formation indicators. For the present section, the facts remain close to observables, absent in the bluest near-infrared band to a strict limit, present with consistent flux in multiple redder bands, and showing red-to-red color ratios that favor a smooth continuum over any combination of heavy dust and extreme emission lines at low distance. The current star formation in MOM-Z14 is inferred from the strength and slope of the continuum redward of the spectral break, because young massive stars emit strongly in the far ultraviolet, and that light, after being shifted by cosmic expansion, falls into the observed near-infrared bands. The method begins with the measured flux density in the first secure red band corrected for the fraction of light that falls outside the photometric aperture, using the locally derived point spread function. That flux density is translated into a luminosity by adopting the favoured distance range from the break placement, and then a widely used conversion between ultraviolet luminosity and star formation rate is applied. This conversion arises from population synthesis models, in which a continuous supply of newly formed stars produces a nearly steady ultraviolet output after a short settling time, and it depends on assumptions about the initial mass function, the metallicity, and the star formation history. Because the data are limited to a few broad bands, the analysis adopts minimal assumptions. A continuous star formation history, over at least several tens of millions of years, a near-solar or subsolar metallicity consistent with early enrichment, and an initial mass function that follows a common form over the massive star range that dominates the ultraviolet light. The continuum slope measured from the red bands, often expressed as a power law, provides a handle on dust attenuation. A bluer slope suggests little dust, while a redder slope suggests some absorption by dust grains. Using an attenuation curve calibrated on star-forming galaxies, the ultraviolet luminosity is corrected upward by a factor that depends on the measured slope and its uncertainty, with the understanding that the curve itself may not be exact for a galaxy at such an early time. In MOM-Z14, the slope is moderately blue within sizable error bars, which points to low or modest dust correction. Nebular emission lines superposed on the continuum can bias star formation estimates if they add flux within one of the photometric bands. Synthetic spectra that include common nebular lines across reasonable ranges of ionization state and metallicity are used to assess this effect. Where the models predict that a single strong line would dominate one band, the observed ratios among the red bands are compared to test for a mismatch. In the present measurements, the ratios align more closely with a smooth continuum than with a line-dominated spectrum, so the bias from lines is treated as a subdominant uncertainty rather than a primary driver. A further correction addresses the possibility that the youngest stars are embedded in dense regions where ionized gas and dust absorb a fraction of their ultraviolet light. The standard ultraviolet conversion partially accounts for such effects, but the exact escape fraction of ultraviolet photons is not measured here, so the residual uncertainty is folded into the quoted range for the star formation rate. The noise properties of the images and the calibration of the photometric 0 points influence the inferred rate through the luminosity and slope. To propagate these effects, the analysis perturbs the fluxes within their uncertainties and recomputes the dust correction and the conversion to star formation rate many times, building a distribution of outcomes from which a central value and credible intervals are reported. Independent reductions that vary background subtraction, aperture size and drizzle parameters produce star formation rates that agree within those intervals, which supports the stability of the inference. Because the ultraviolet method traces the average formation of massive stars over a timescale of several tens of millions of years, it smooths over short bursts or lulls. If MOM-Z14 is experiencing a brief burst, the ultraviolet luminosity will overestimate the long-term average. If it has recently quenched, the luminosity will underestimate the peak activity. The present data do not measure rapid time variability, so the rate reported here should be read as a time-averaged indicator rather than an instantaneous count. Stochastic sampling of the high mass end of the initial mass function can also alter the ultraviolet output for very small systems, but the luminosity of MOM-Z14 suggests that many massive stars contribute, which reduces this source of variance. The role of the intergalactic medium in absorbing flux blueward of the Lyman-alpha transition is already accounted for by restricting the continuum fit to redder wavelengths, so it does not directly suppress the ultraviolet continuum used for the rate. Gravitational lensing, if present, would amplify the observed fluxes and inflate the inferred rate. A preliminary check for lensing is presented later in the script. Until that check is complete, the star formation rate remains conditional on the assumption of negligible lensing amplification. The conversion from luminosity to rate assumes a known distance. The redshift probability distribution therefore propagates into the rate uncertainty, with higher distance implying a higher luminosity for the same observed flux. The resulting star formation rate for MOM-Z14 after dust correction, within the bounds allowed by the continuum slope and after marginalizing over flux and distance uncertainties, lies in the range that is common for compact galaxies in the early universe of comparable brightness. In everyday terms, it corresponds to the formation of roughly a few to perhaps several tens of solar masses of stars per year, with the exact number limited by the assumptions and by the depth of the data. This rate places the object among actively building systems rather than quiescent remnants, consistent with its blue continuum and compact appearance. The inference remains tied closely to observables and to established conversions. It does not rely on detailed spectral features, it does not require a complex star formation history, and it does not claim a precise rate beyond what the data justify. The limits are clear. Noise and calibration set the floor on accuracy, dust and escape fraction, add systematic breadth. Emission lines could contribute modestly, distance uncertainty introduces a scaling, and any undetected lensing would shift the entire range. Within these bounds, the ultraviolet continuum supports the conclusion that MOM-Z14 is converting gas into new stars at a meaningful pace at the observed epoch, and this conclusion will serve as a foundation for later steps that consider the growth of stellar mass and the timescales implied by this activity. The estimated stellar age of MOM-Z14 is approached with models that relate the observed continuum to the duration of star formation, while restricting assumptions to what the data can support. The continuum measured redward of the spectral break samples, the rest frame far ultraviolet where short-lived massive stars dominate the light. If star formation began only a few million years ago, in a brief burst the continuum would appear extremely blue, and the accumulated mass in longer-lived stars would be small. If star formation has persisted for several tens of millions of years, the continuum remains blue, but the underlying population gains a more balanced mix of stellar lifetimes, which raises the mass-to-light ratio without producing a pronounced redwood feature. If star formation has continued for longer, still the build-up of older stars begins to carve a modest 400 nanometer break in the rest frame optical that would shift into bands redder than those used here. In the present data, that feature is not securely detected, so very old solutions are not favoured. The fitting procedure therefore scans a set of population histories that span a single burst, a constant rate, and gently rising or gently declining rates. Distance is taken from the break placement with its credible interval dust attenuation, is allowed to vary across curves calibrated on star-forming galaxies, and metallicity ranges from very low values to moderately subsolar values. For each trial history and parameter set, the model computes synthetic fluxes through the same filters and compares them to the measured fluxes and limits, building a probability distribution for age and stellar mass. The solutions that match the blue continuum with little curvature typically yield ages of several tens of millions of years under constant or gently rising histories. Pure bursts younger than about 5 million years can also fit the continuum slope, but tend to predict stronger nebular line contributions that would produce irregular color ratios among the red bands. Such patterns are not seen within present uncertainties. Very old solutions extending to a few 100 million years would raise the mass-to-light ratio enough to demand a larger stellar mass than what the ultraviolet luminosity supports at the favoured distance, and they risk producing a redder continuum than observed unless dust is set to nearly zero. The template fits find little improvement in likelihood when pushing to those ages, so the posterior weight remains concentrated at young to intermediate values. A helpful cross-check arises from the relation between stellar mass and star formation rate, implied by the models. For a roughly constant rate, the stellar mass equals the time integral of that rate, reduced by the mass that evolving stars return to gas. Using the rate inferred from the ultraviolet continuum, and adopting a return fraction consistent with standard stellar evolution, the time required to assemble the mass indicated by the preferred templates lies in the same range of several tens to roughly 100 million years. Gently rising histories shorten the needed time somewhat, while gently declining histories lengthen it, but all remain within that general band. This agreement between the light-based age and the growth time based on the rate strengthens the interpretation. Dust and metallicity introduce degeneracies that can mimic age effects, and they are addressed explicitly. Dust attenuation can redden a young population and make it look older. Low metallicity can make an older population look bluer. The measured continuum slope is moderately blue with sizable uncertainty, which disfavors heavy dust. When dust is increased to levels that would markedly redden the continuum, the templates require compensating changes in age or metallicity that either worsen the fit to the red band ratios or push the mass to light ratio beyond what the luminosity budget can support. When metallicity is reduced to very low values, the continuum becomes somewhat bluer for a fixed age, but the improvement is small compared with the observed error bars, and the inferred ages do not collapse to the youngest limit. The posterior distributions for dust and metallicity therefore remain broad, but avoid the extremes, and within that space the age remains anchored near young to intermediate values. The absence of a strong 400 nanometer break in the available band supplies another gentle constraint. If a dominant component older than about 100 million years were present, the combined spectrum would begin to show a redder curvature beyond the near-infrared bands used here. Since the data do not display such curvature at significant confidence, the fraction of very old stars is limited. This does not exclude a minority contribution from older stars, but it argues against a scenario in which an ancient population dominates the mass while a tiny recent burst dominates the light. Nebula continuum and line emission can bias age estimates by filling in parts of the spectrum and altering color ratios. The fits therefore include nebula emission tied to the ionizing photon output predicted by each model. Solutions that rely on very strong lines to reproduce the colors tend to create mismatches among adjacent red bands that are not present in the measurements, so the allowed contribution from lines remains moderate and does not overturn the age bounds. Calibration and distance systematics are propagated by perturbing photometric 0 points, effective wavelengths, and redshift within their uncertainties and repeating the fits. The credible interval for age broadens but remains centered in the same range. Independent reductions that vary background subtraction, aperture definition, and drizzle parameters recover similar age distributions, which supports robustness to methodological choices. The cosmic time at the favored distance sets an absolute ceiling since the universe is only a few 100 million years old at that epoch. Ages that approach the cosmic limit are not required by the fits and are downweighted by the absence of the redwood features they would imply. The resulting picture is consistent and deliberately conservative. MOM-Z14 hosts a young to intermediate stellar population formed over several tens to roughly 100 million years with low to modest dust, low to moderately subsolar metallicity, and no secure evidence for a dominant older component. The associated stellar mass increases toward the older edge of this interval and remains compatible with the ultraviolet luminosity after accounting for mass loss and the distance range. These bounds will guide the next steps that examine metals and dust more directly, while carrying forward the recognized degeneracies and uncertainties that link age composition and attenuation in the faint light of so early a system. Metals and dust in MOM-Z14 are inferred indirectly from the colors and from the shape of the continuum because discrete spectral features that would pin down composition fall outside the bands used here or lie below current sensitivity. The measurements show a pronounced drop in flux shortward of the hydrogen Lyman-alpha transition and a smooth, moderately blue continuum longward of that break. This pattern already limits the amount of dust that can be present since heavy dust would redden the continuum substantially and would drive the red band ratios away from the observed sequence. The ultraviolet slope derived from the flux ratios of the red detections is negative with broad but meaningful uncertainty, a sign that the continuum tilts towards shorter rest wavelengths rather than curving upward. Under standard attenuation, curves calibrated on star-forming galaxies such as curves similar to those measured in the Small Magellanic Cloud and in local starbursts. This slope corresponds to low or modest dust attenuation. When those curves are applied in population fits the preferred colour, excess remains small. Pushing the dust to larger values forces compensating changes in age and metallicity that worsen the match to the red band ratios or to the overall luminosity at the favoured distance. The absence of a measurable curvature across adjacent red bands further argues that any dust reddening is gentle rather than strong, because strong reddening tends to create a more pronounced bending of the continuum across the wide filters used here. Metallicity is entangled with dust and age in ways that are carefully accounted for in the fits. Lower metallicity reduces the opacity of stellar atmospheres and yields a bluer intrinsic continuum for a given age, while higher metallicity produces redder light at fixed age. The template library spans very low metallicity to moderately subsolar metallicity, and ties nebular emission to the ionizing photon output expected at each metallicity. Solutions with extremely low metallicity approaching the metal-free limit can in principle reproduce very blue slopes, but they also predict strong nebular contributions that would imprint uneven structure on the red band ratios. The present measurements do not require such structure. Solutions with moderately subsolar metallicity and little dust reproduce the observed smooth rise more naturally while still allowing a range that reflects the broad uncertainties. Very high metallicity is disfavored at this early epoch on both physical and observational grounds. Physically, it demands a level of prior enrichment that would be difficult to achieve within the short cosmic time available. Observationally, it tends to redden the continuum beyond what is measured unless dust is driven to near zero and the age is tuned to remain very young, a combination that lowers the mass-to-light ratio and strains the energy budget implied by the luminosity and distance. None of these disfavored corners of parameter space yields a marked improvement in likelihood. The lack of strong emission line signatures within the red bands also informs the balance of metals and dust. Lines such as oxygen 3 at 500 nanometers and hydrogen beta, which at very high distance would shift into wavelengths redder than those sampled here, are not directly measured, so their absolute strengths remain unknown. However, the shapes of the red band spectral energy distribution disfavor a spectrum dominated by a single line, because that would create a jagged sequence of fluxes that is not seen. This does not rule out moderate lines consistent with ongoing star formation. It simply means that the continuum dominates the broad band light at the current depth. Nebular continuum emission, which can add a smooth component longward of the break, especially at low metallicity, is included in the models and modestly alters the derived dust and metallicity ranges, but it does not overturn the conclusion that dust attenuation is likely small and metallicity is likely low to moderately subsolar. A further constraint arises from the absence of a detected 400 nanometer break in the rest frame. If an older metal-rich population dominated the light, that break would begin to shape the continuum that falls into the redder observed bands. Since the current data do not show such curvature, the fraction of old metal-rich stars must be limited. This is consistent with a young or gently rising star formation history, in which metals have been produced by earlier short-lived stars, but have not yet built up to solar abundance. The analysis also considers the role of the intergalactic medium, which strongly absorbs light shortward of the hydrogen transition, and can be confused with dust if not treated separately. By fitting the continuum only longward of the break and by allowing the blue side to be fully absorbed, the method isolates dust effect from intergalactic absorption. Any residual uncertainty in how sharply the break falls affects the distance estimate more than the dust estimate, since dust acts across the red bands, while the break position acts at the boundary between detection and non-detection. External checks that could refine the dust and metal picture are noted even if they are not yet available. A detection of the rest frame optical continuum would anchor the 400 nanometer region and yield a more precise constraint on older stars and on metallicity-sensitive features. A measurement of sub-millimeter emission would probe the thermal glow of dust grains and would set a more direct upper limit on dust mass and on obscured star formation. In their absence, the present inferences remain conservative and based on the observed near-infrared continuum alone. The emerging picture is simple and bounded by data. MOM-Z14 likely contains little dust by the standards of later galaxies, and its metals are likely below the solar value, consistent with a system only a short time removed from its first rounds of enrichment. The precise values remain uncertain because a narrow set of bands cannot break all degeneracies, yet the allowed range excludes heavy dust reddening and excludes metallicities so high that they would force a redder continuum than measured. These constraints feed directly into the interpretation of star formation and age, and will inform the assessment of ionized gas and candidate emission lines in the next step, where the conditions of the gas are examined against the limits set here by the faint smooth light of the stars. Traces of ionized gas in MOM-Z14 are investigated with the same observations that establish its continuum, since young massive stars emit photons energetic enough to ionize hydrogen and heavier elements, and the gas that recombines can imprint subtle features in broad bands and in low-resolution spectra. The most direct signature would be an emission line that lifts the flux in a single red band relative to its neighbours, or produces a shallow crest in a slitless spectrum at a wavelength consistent with the rest ultraviolet transition shifted by the favoured distance. The search begins in the imaging by comparing the measured flux in each red band with the smooth continuum expected from a single power law. A synthetic continuum anchored to the two faintest red detections predicts the flux in the remaining red band, and the residual is tested against the noise model that includes photon noise, background variance and covariance introduced by image combination. No single band shows a statistically secure positive excess after accounting for the small correlations between bands, which argues against a dominant line falling wholly within one filter. To check sensitivity, artificial lines are injected into the images as narrow features broadened by the point spread function and by the filter width with flux chosen to span the range of equivalent widths commonly reported in very early galaxies. The recovery procedure finds that a line with very large equivalent width would have been detected as a band excess at the current depth, whereas a moderate line would not rise above the uncertainties. MOM-Z14 falls in the regime where only the strongest line would be visible in broadband photometry. A complementary test uses the slitless spectrum when available. The disperser spreads the light so that any discrete feature appears as a gentle bump broader than its intrinsic width. Because resolution is modest, and the extraction aperture encompasses light already blurred by the point spread function, the extraction pipeline subtracts the background mask's overlaps using positions from the imaging catalogue and propagates an error array that tracks photon noise and residual structure. Within this spectrum, the continuum break that marks the transition from non-detection to detection is the dominant feature. Redward of the break, the spectrum is consistent with a smooth slope within uncertainties, and no crest rises above a conservative threshold that accounts for multiple trials across wavelength. The wavelength intervals examined include where rest ultraviolet lines, such as carbon-3, oxygen-3, and helium-2, would appear if their strengths were large. The absence of a secure crest at those positions does not prove that the lines are absent. It sets limits that depend on the resolution, the extraction, and the noise, and those limits are recorded for use in later synthesis. Hydrogen Lyman-alpha emission receives special attention. The same intergalactic medium that erases the continuum blue ward of the transition strongly scatters and absorbs this line when the neutral fraction is high. At the early times favoured by the break position, a high neutral fraction is expected, so a non-detection is not surprising. The spectrum is nonetheless examined for a narrow rise immediately redward of the break, and for asymmetric shapes that sometimes survive partial transmission through patchy neutral gas. No such feature is found at significant confidence, and the imaging shows no indication of a narrow band enhancement, confined to the first red detection. These results align with the expectation that hydrogen Lyman-alpha is strongly suppressed at this epoch, but the data do not measure the neutral fraction. They only show that MOM-Z14 does not display a bright line. The continuum itself can carry the imprint of ionized gas through nebular continuum processes that add smooth light longward of the break. Free bound and free emission and 2-photon emission can elevate the continuum slightly depending on gas density and on the rate at which young stars produce ionizing photons. The population fits include such nebular components tied to the inferred star formation rate. Allowing this contribution changes the preferred continuum slope by less than 1 standard deviation and shifts the dust correction only modestly, which indicates that nebular continuum is not large enough at the present depth to alter the principal conclusions drawn from the colours. Possible false positives and false negatives are addressed with methodical checks. Correlated noise introduced by image combination is measured with empty apertures and folded into the photometric errors used for the line search. Photometric 0 points and effective wavelengths are perturbed within calibration uncertainties, and the excess tests and spectral fits are repeated. No band acquires a significant positive residual, and no spectral crest becomes compelling. The spectral background is refit with alternative smooth functions, and the extraction aperture is varied slightly to test sensitivity to the trace width. The resulting flux vectors remain consistent with the smooth continuum. Contamination from overlapping spectral traces is constrained by using the imaging to predict where neighbours fall along the dispersion and by subtracting their modelled contributions. Residuals near the expected locations of strong rest. Ultraviolet lines are not systematically positive after this subtraction. Upper limits on candidate line fluxes are then translated into limits on equivalent widths under the adopted distance range. These limits depend on the assumed continuum level and on the filter transmission for the imaging case and on the extraction throughput for the spectral case. The bounds allow nebular lines of moderate strength that would be compatible with the measured star formation rate, and with low to moderately subsolar metallicity, and they disfavour the very extreme equivalent widths, sometimes reported in younger or lower metallicity systems. The mapping from limits to physical conditions is degenerate without direct measures of gas density and temperature, so the present section reports observational bounds rather than derived parameters such as ionization parameter or electron density. Taken together, the facts are conservative and remain close to the data. No secure emission line is detected in the imaging or in the low-resolution spectrum. The continuum is smooth enough to exclude the strongest lines at the current sensitivity. The lack of a hydrogen Lyman-alpha crest is consistent with strong absorption by a largely neutral intergalactic medium at early times. Within these limits, ionized gas is expected on physical grounds and is compatible with the observed ultraviolet continuum, but its discrete spectral signatures are not yet measured. These results conclude the gas and ionization view at the present depth and set the stage for the next inward step, which tests whether gravitational lensing could alter the apparent brightness, and thus the interpretation of all flux-based quantities reported so far. The intrinsic luminosity of MOM-Z14 is established by testing whether gravitational lensing could have boosted the observed flux because a foreground mass distribution can magnify a background source without changing its surface brightness. The first check inspects the field for obvious signs of strong lensing such as arcs, mirrored pairs, or multiple compact images with identical colors arranged about a plausible center of mass. The images show no curved features at the depth where arcs would stand out, and there is no second point with the same sharp spectral break and the same red-to-red color sequence within a radius where a simple lens would produce counter-images. Positions and fluxes of all red-selected neighbors are compared pairwise. None forms a symmetric configuration that would suggest a common origin. The absence of such geometry does not rule out moderate magnification by weak lensing, but it reduces the likelihood of the large factors produced near critical curves. A second check considers the alignment with foreground galaxies that could act as lenses. Every object within several arc seconds that is bright in the bluest near-infrared band or in shorter wavelength images is treated as a potential deflector and assigned a broad distance estimate from its colors. Those estimates place several candidates at modest distances, but their stellar masses inferred from their brightness are limited, and their projected separations from MOM-Z14 are large enough that any single galaxy lens would produce only small magnification at the source position. The nearest such galaxy shows regular isophotes and no signs of a massive halo dominating the local field. Its light profile declines smoothly with radius, and MOM-Z14 does not lie along any visible structure that would suggest an organized group potential. A third test uses the invariance of surface brightness under lensing. Because lensing preserves surface brightness, while scaling angular size and flux together, a magnified object appears larger and brighter by the same factor. The measured half-light radius of MOM-Z14 is only slightly larger than the stellar point spread function, which indicates that the source is barely resolved. If a large magnification were present, the implied unlensed object would be proportionally smaller and could become unresolved to a degree inconsistent with the observed marginal extension. Conversely, if the observed size were itself magnified, then the intrinsic size would be even smaller, and the surface brightness would be unchanged. The measured combination of high compactness and moderate total flux does not demand magnification. It is compatible with an unlensed compact galaxy at very early times. To make this argument quantitative, the analysis compares MOM-Z14 to the size luminosity trend observed among high-distance candidates selected with similar criteria. When placed at the favoured distance, its angular size and brightness fall within the envelope occupied by comparable objects that show no lensing flags, rather than in the tail of sources that are suspiciously bright for their size. This comparative placement does not rely on detailed modelling of structure. It uses the broad empirical fact that strongly magnified sources tend to sit above the main sequence of brightness at a given apparent size. The fourth test addresses weak lensing convergence along the line of sight. Even in the absence of a dominant deflector, the cumulative effect of large-scale structure can shift flux by a modest factor. The field is scanned for concentrations of foreground galaxies with similar colours that might trace an overdensity, and no cluster-scale grouping emerges within the region that would exert a large convergence. The number counts of blue galaxies across the image are uniform within statistical scatter, and there is no excess of bright galaxies near MOM-Z14 that would mark a projected group. While these image-based checks cannot measure the exact convergence they make, strong lensing unlikely, and confine the plausible magnification to a range near unity. A fifth and complementary test compares the morphology measured in the two reddest bands. Lensing shear would stretch the image coherently, creating an aligned elongation that persists across bands. The isophote fits find axis ratios consistent with unity within large uncertainties, and the position angle is poorly defined, which argue that any shear is small. Rotationally average profiles match the expectations for a nearly round source, blurred by the instrument rather than for a tangentially stretched arc segment. These shape-based checks are limited by the barely resolved nature of the source, but within that limit they show no pattern indicative of shear. Another indicator comes from the stability of the centroid across dithers and reductions. Residual astrometric distortions coupled with lensing can cause slight shifts between bands if differential refraction or chromatic point spread, function variations interact with the stretch source. The measured centroids agree to within a small fraction of a pixel in all red bands, which reduces the room for such complex interactions. Possible counterarguments are considered in turn. It is possible that a small foreground satellite or a faint dark halo with little light lies very close to the line of sight and provides moderate magnification without obvious imaging signatures. This scenario cannot be excluded by the present data, yet the probability of a near-perfect alignment with a low luminosity deflector is small, and the magnification it would induce is unlikely to exceed a factor of a few. The uncertainties carried forward for luminosity therefore include a margin that accounts for undetected modest magnification, but they do not inflate to allow the very large factors associated with strong lensing near critical curves. The translation from observed flux to intrinsic luminosity then proceeds by adopting the favoured distance range and by treating the lensing factor as unity with an allowed perturbation that spans weak lensing values. Photometric calibration uncertainties and distance probability are propagated simultaneously. The outcome is a luminosity consistent with compact actively star-forming galaxies at very early times, and not so extreme as to require amplification. This conclusion is provisional in the sense appropriate to the data. Deeper imaging could reveal subtle arcs or faint counter-images, and spectroscopic measures of foreground galaxies could refine their masses, and thus the expected convergence. For the present evidence, the image plane geometry, the absence of arc-like features, the lack of a foreground mass concentration at small separation, the nearly round morphology across bands, the surface brightness considerations, and the comparative placement in the size-luminosity plane all support the working assumption that MOM-Z14 is not strongly lensed. The intrinsic luminosity derived under that assumption becomes the basis for later comparisons to prior records and for the interpretation of physical parameters that scale with true brightness. Verification of the signal from MOM-Z14 proceeds through a sequence of tests designed to exclude artifacts processing errors and spurious detections with procedural detail introduced only where it secures the conclusion. The starting point is a reproducibility check across independent reductions that differ in background modeling, cosmic ray rejection, astrometric alignment, and image combination kernels. In each path, the candidate is detected at consistent significance in the red bands and remains undetected in the bluest band to a comparable upper limit, which establishes that the signal is not the product of a single tuning choice. Detector-level artifacts are addressed next. Hot pixels and transient events are rejected by the dithered observing pattern, which steps the sky across the detector so that fixed pixel defects land at different image coordinates. The stacking process employs outlier rejection keyed to the local noise, and a review of the individual calibrated frames shows no single exposure in which an isolated pixel drives the source. Rather, a compact cluster of positive values appears at the same sky position across many frames. Persistence from bright sources is a known risk in infrared arrays. To counter this, the frames immediately preceding the target exposures are examined for saturated stars or extended bright objects at the detector positions that later hold the candidate. No such precursors are present within the persistence time window, and a mask of pixels prone to persistence shows no overlap with the candidate footprint. Electronic crosstalk and channel-dependent bias structures are tested by comparing the signal when the source falls on different amplifier regions due to dithering. The measured flux varies within the expected statistical range and shows no systematic level shifts tied to readout boundaries. Flat field and gain nonlinearity errors can imprint false structures if the calibration is inaccurate. The flat field solution is perturbed within its stated uncertainty, and the photometry is repeated. The flux changes remain below one standard deviation. The peak pixel values lie well within the linear response range, and a linearity correction applied, and withheld yields indistinguishable results within the noise. Background subtraction is a frequent source of false positives for faint sources. Local skies measured in annuli around the candidate and in many blank aperture across the field. The distribution of those sky values is symmetric and centered near zero after standard calibration with variance matching the noise model. When the sky-fitting scale is varied, and when large-scale gradients are permitted in the model, the recovered flux for MOM-Z14 shifts by amounts smaller than the propagated uncertainty. A negative test constructed by inverting the stacked images produces a symmetric distribution of negative peaks with no negative counterpart at the candidate position, which argues that the photometric aperture is not aligned with a background dip. Astrometric alignment is verified by cross-correlating stellar positions between bands and between temporally separated subsets. The alignment residuals are a small fraction of a pixel, and the centroid of MOM-Z14 is consistent between red bands and between subsets, which excludes a false color pattern caused by misregistration. The bluest band non-detection is tested for hidden flux that might be smeared by small misalignments. Forced photometry at the red band centroid returns values consistent with zero within 2 standard deviations, even when the aperture is broadened to accommodate a conservative alignment error. The model of the point spread function underlies aperture corrections and morphology. Stars across the field are used to construct an empirical point spread function at the position and time of the observations, and variation with subpixel centroid is characterized. Applying this model yields aperture corrections that bring isolated stars to consistent totals. When a different kernel is used to combine exposures which changes correlated noise, and the point spread function wings, the corrected flux of MOM-Z14 remains the same within uncertainty, showing that the detection does not rely on a particular representation of the blurring. Source segmentation and deblending are tested by altering the detection threshold, the minimum contrast for splitting, and the dilation radius that defines the footprint. The candidate remains a single segment with a stable footprint across these choices, and no nearby source merges or splits in a way that would create or destroy the detection. To control the false discovery rate, artificial noise only stacks are generated by randomly rotating and shifting the input frames before combination, which preserves noise properties while washing out real sky sources. Running the identical detection pipeline on these stacks yields the expected number of spurious peaks above the chosen threshold, and none aligns with the candidate position more often than random expectation. Injection and recovery tests place simulated sources with the measured size and a range of fluxes into the real images, then repeat the full detection and photometry chain. The completeness curve shows high recovery probability at the measured flux, and the purity estimate indicates that sources with the measured colors are rarely produced by noise fluctuations or by common backgrounds. To probe whether a bright undetected neighbor could scatter light into the aperture, the local scene is modeled with profiles of nearby objects mirrored across the candidate and subtracted. The residual flux within the aperture changes by much less than one standard deviation, indicating that the measurement is not driven by structured wings from a neighbor. Time domain stability is addressed by splitting the data into two halves, separated in time and by detector position. In both halves, the candidate is detected in the red bands with consistent flux and shape, and absent in the bluest band within consistent limits. A difference image between halves near the source position shows no residual, which argues against a transient or variable artifact. Photometric calibration is an overarching concern. 0 points are perturbed within their uncertainties and the flux is rescaled. Colors remain within the same region of color space that defines the high distance selection. Effective wavelengths are shifted within their tolerances and the break placement fit is repeated. The favored interval moves by less than the quoted bound. Finally, the slitless spectrum, when present, is processed with two independent extractions that differ in background modeling and contamination masking. Both display a continuum break aligned with the photometric step and no discrete crest above a conservative threshold redwood of the break. When the trace width is varied, the location of the break remains stable within the error array. No single check is decisive in isolation, but together they form a consistent picture. Across reductions, across time, splits across detector regions, and across methodological choices, a compact source persists in the red bands. At the same sky position remains absent in the blue band to stringent limits, and resists interpretation as a detector artifact, a processing error, or a spurious noise peak. These verified properties lock the signal as real within the limits of the present data, and prepare a fair placement against prior records. Placement of MOM-Z14 against prior records proceeds by defining clear and consistent criteria, and then comparing like with like. The metric is the earliest cosmic epoch reached by a galaxy candidate whose distance estimate rests on a robust discontinuity between non-detection in a bluer band and secure detection in redder bands, optionally supported by a low-resolution spectrum that shows a concordant break. A second criterion distinguishes between photometric candidates, which rely on colors and upper limits, and spectroscopic conformations which identify a break or a line in dispersed light with understood resolution and background. A third criterion excludes systems whose apparent brightness is likely magnified by strong gravitational lensing, because magnification does not change distance, but can bias selection and follow up. With these rules established, the literature of the early years of the new observatory shows a sequence of increasingly distant galaxies culled from deep surveys. Several well-known sources achieve redshifts in the low teens by photometric methods, and a smaller subset reaches similar territory, with spectroscopic confirmation of a continuum break or of a weak line that brackets the same epoch. A handful of objects have been proposed at even higher photometric redshift, but many of those rely on marginal non-detections or on color combinations that can be mimicked by dusty interlopers at lower distance, and subsequent analyses often reduce their favored distance or flag them as uncertain. Against this backdrop, the evidence for MOM-Z14 takes the form described in earlier sections: a stringent non-detection in the bluest near-infrared band, high significance detections in at least 2 redder bands a step in flux that aligns with the expected position of the hydrogen break for an epoch in the mid to high teens in redshift, and a smooth redwood continuum without jagged structure, indicative of extreme line contamination. When a low-resolution spectrum is available, it shows a downturn at a wavelength consistent with the photometric step within errors that reflect finite resolution and careful background modeling. The favored distance probability distribution for MOM-Z14 peaks beyond the central values reported for earlier confirmed galaxies and retains most of its credible weight above those values when calibration and template uncertainties are propagated. This placement is not asserted by a single number, but by the overlap or lack of overlap between probability ranges. To ensure a fair comparison, the same priors on dust metallicity and star formation history are used when the analysis is repeated for representative prior record holders, and the same treatment of upper limits is applied to all. Under these matched assumptions, MOM-Z14's break falls at a longer observed wavelength than the breaks that anchored the previously confirmed set, shifting its probability mass to earlier cosmic time. The distinction from the leading photometric candidates that were not confirmed rests on data quality and on internal consistency. In those earlier cases, the non-detection band sometimes had shallow depth relative to the detection bands, so that small calibration shifts could move the solution toward lower distance. In other cases, the ratio of adjacent red band fluxes hinted at line-dominated spectra that can masquerade as a high break. MOM-Z14 differs in that the bluest band reaches depth comparable to the red bands as measured in matched apertures. The non-detection remains a strong constraint under forced photometry, and the red band ratios align with a smooth continuum within the noise covariance which narrows the room for low-distance solutions. The lensing criterion is also relevant. A few ultra-distant candidates in the past were found behind foreground clusters, raising reasonable concerns about magnification and multiplicity. For MOM-Z14, the imaging shows no arcs or mirrored companions. The local field lacks a concentration of massive foreground galaxies. The morphology is nearly round across bands, and surface brightness considerations do not demand magnification. This does not change the distance, but it enhances the comparability to unlensed field records that set the common standard. A quantitative benchmark uses the probability that the true redshift of MOM-Z14 exceeds the central redshift of the most distant previously confirmed object. That probability is computed by integrating the distance posterior of MOM-Z14 above the earlier central value while marginalizing over calibration and template uncertainties. The result is high enough to claim that MOM-Z14 surpasses the prior record under the adopted criteria. The same exercise repeated with the earlier object's credible interval lowers the probability but does not erase the preference, unless one adopts extreme calibration, shifts outside their stated tolerances, which the analysis does not. Because the field advances quickly, the comparison is also stress-tested against independent reductions. When different pipelines measure slightly different fluxes, MOM-Z14's favoured distance shifts by a small fraction, yet it remains beyond earlier central values within their intervals. A conservative reading of the ensemble is that MOM-Z14 either sets a new record outright, if one requires concordant photometry and a spectral break, or it ties the record within errors if one inflates the bounds to include the most cautious calibration allowances. In neither framing does it fall below the prior confirmed tier. The physical properties inferred at that distance, such as compact size and a moderate star formation rate, are comparable to those reported for the previous leaders when scaled to their own distances, which removes any suspicion that an implausibly luminous or extended outlier is driving the claim. Instead, the record arises from the position of the spectral break across well-characterized filters from the strength of the non-detection relative to the detections, and from the absence of features that would redirect the solution toward lower distance. This placement is recorded with explicit caveats that the field may produce deeper spectra and new candidates. For the present data, and with matched criteria, MOM-Z14 resides beyond earlier confirmed galaxies in cosmic time, displacing the boundary of the observed universe a small but measurable step outward and establishing a new reference point for models of early assembly that will be examined in the next section. The properties of MOM-Z14 set concrete checkpoints for models of early galaxy formation that aim to reproduce how stars first assemble, how metals appear, and how light escapes into a largely neutral intergalactic medium. The first checkpoint is the timing of assembly. The preferred distance places MOM-Z14 within the first few 100 million years after the beginning of cosmic expansion, so models must produce compact star-forming systems by that time without invoking unusual conditions. This means the median halo growth in simulations should already host cooling gas dense enough to form young stellar populations with star formation rates of a few to several tens of solar masses per year, while remaining consistent with the observed moderate luminosity and small angular size. Any model that delays the onset of efficient cooling, or that requires rare fluctuations to trigger the first sustained star formation, would underproduce objects like this one at the observed epoch. The second checkpoint concerns size and internal structure. MOM-Z14 is barely resolved and consistent with a shallow central concentration, which implies that its stars and gas occupy a very small physical scale when converted from angular to linear units under the favored distance. Models must recover such compact light distributions without predicting excessive central cusps or extended diffuse halos that would have been detected at the present surface brightness depth. Feedback from young stars must be strong enough to prevent runaway central densities that would sharpen the profile beyond what is observed, yet not so strong that it evacuates the core and leaves only a broad remnant. The third checkpoint involves the star formation rate relative to the stellar mass and age bounds. The ultraviolet continuum indicates a time-averaged rate consistent with several tens of millions of years of activity. Cosmological models that implement star formation prescriptions must yield similar ratios between current rate and assembled mass when integrated over the same timescales, and when filtered through observational selection that favors systems with strong breaks and smooth redwood continua. If models predict either very bursty histories that overproduce extreme emission lines, or very quiescent histories that underproduce ultraviolet flux at fixed mass, they will miss the locus occupied by MOM-Z14. The fourth checkpoint addresses metals and dust. The colors favor low to moderately subsolar metallicity and small dust attenuation. Simulations of chemical enrichment must produce rapid but not excessive metal, build up consistent with a few generations of short-lived massive stars enriching the gas without yet reaching solar abundance. Dust formation and destruction need to be efficient enough to allow some growth, while leaving the continuum only mildly reddened. If models generate heavy dust by this epoch, they would predict redder slopes and stronger curvature than measured. If they suppress dust entirely, they must still reproduce the moderate blue slope rather than an extremely blue spectrum that the data do not require. The fifth checkpoint covers nebular emission and ionization conditions. The lack of a strong line excess in any single band, and the smooth low-resolution spectrum, redwood of the break, imply that at the current sensitivity extreme equivalent widths, are not present. Models that tie ionizing photon production to star formation metallicity and stellar rotation should therefore predict moderate nebular contributions consistent with the upper limits, while leaving room for lines that fall below detection. The absence of a prominent hydrogen Lyman-alpha crest is fully compatible with a highly neutral intergalactic medium at this epoch, so ionization models are not pressured to provide early large-scale ionized bubbles around every star-forming source. The sixth checkpoint concerns the escape of ultraviolet light. MOM-Z14 is bright enough in the far ultraviolet rest frame to suggest that a meaningful fraction of stellar light exits the galaxy, yet the smooth continuum indicates that strongline-dominated leakage is not required. Models must balance internal absorption by gas and dust with geometric pathways that allow continuum photons to escape along at least some sightlines. Overly opaque interiors would dim the object below the observed flux. Overly transparent interiors coupled with extreme star formation would produce features not seen. The seventh checkpoint involves gravitational lensing and number densities. The evidence disfavors strong lensing for MOM-Z14, which means its brightness represents a typical intrinsic value for compact systems at this epoch. Models that predict the abundance of such galaxies must match not only the presence of a single object, but also the expected surface density in deep fields after accounting for survey volume detection thresholds and color selection. Overabundance would imply too rapid growth or too efficient star formation. Scarcity would imply the opposite. The eighth checkpoint links stellar populations to ionization budgets. While this section does not compute the total ionizing photon output, the combination of a young to intermediate age, low to modest dust, and a moderate star formation rate provides a credible photon supply. Models must place similar objects at sufficient densities to contribute meaningfully to the rising ionization fraction without relying on rare extreme systems. The ninth checkpoint concerns kinematics indirectly. Although no velocity information is measured here, the compactness and the sustained star formation suggest gas reservoirs that are dense and gravitationally bound. Simulations should avoid predicting violent fragmentation that would produce obvious substructure at current resolution, yet they should allow inflows and outflows that regulate the compact light profile and the moderate dust content. The 10th checkpoint is methodological and addresses robustness. The model comparisons should be performed by forward modeling into the observed bands, rather than by comparing intrinsic rest frame properties alone. When models generate mock catalogues and images that are processed through the same selection and measurement steps, the locus of size, color, and brightness, where MOM-Z14 resides, must be reproduced within the stated uncertainties. Meeting these checkpoints does not require new physics. It requires that existing prescriptions for cooling star formation feedback, enrichment, and dust creation operate quickly and coherently in the smallest early halos. The object does not demand exotic populations or unusual initial mass functions under the current data, but it does require that assembly proceeds efficiently in environments only a short time removed from the first light. As a result, MOM-Z14 functions as a clear target for models, produce compact, moderately luminous, lightly reddened galaxies with young to intermediate populations and modest nebula signatures at a cosmic time consistent with the measured break, and do so with number densities that agree with deep survey statistics. This concrete ledger of requirements frames the theory response while future observations tighten each bound. The dominant uncertainties that shape the interpretation of MOM-Z14 arise from measurement limits, calibration systematics, modeling choices, and residual astrophysical degeneracies, and each uncertainty affects specific inferences in a traceable way. Photometric calibration sits first among them because small shifts in 0 points and effective wavelengths propagate directly into colours the placement of the spectral break and the continuum slope that informs dust correction and star formation rate. The analysis bounds these shifts within the stated calibration tolerances and folds the resulting spread into the redshift probability. Yet a remaining margin persists and widens all derived ranges. Filter transmission curves introduce a related uncertainty, since broadband filters integrate over wide intervals, and small errors in their shapes can move the apparent break position by a fraction that matters at very early epochs. This affects the central redshift and thereby the luminosity distance that scales intrinsic brightness, star formation rate, and stellar mass. Noise properties and covariance introduced by image combination are another source because correlated noise can depress or elevate fluxes coherently across bands. The pipeline estimates this covariance from empty sky stacks and inflates errors accordingly, but imperfect knowledge of the covariance matrix can still bias the significance of the non-detection in the bluest band and the weight assigned to each red detection. Background subtraction and flat fielding systematics can mimic faint structures or remove real flux at low surface brightness. Tests that vary background fitting scales and perturb the flat fields find stable results within uncertainties, yet any residual large-scale pattern would mostly influence measurements near the detection threshold and thus affects the confidence of the break and the slope more than the total flux in the brightest band. Astrometric alignment also enters because subpixel shifts between bands can smear a faint source and leak flux into or out of matched apertures. Forced photometry at the red band centroid and checks of alignment residuals reduce this risk, but an undiagnosed offset at the level of a small fraction of a pixel would change color ratios slightly, and thus alter dust corrections and the continuum slope. The extraction of the low-resolution spectrum adds separate uncertainties tied to background modeling, overlap subtraction, and aperture width. These control whether a shallow crest could be mistaken for a real line or whether a smooth continuum could be biased near the break, and the analysis uses two extractions to bound such effects, but modest residuals remain and broaden the allowed redshift interval. Template-based interpretation introduces modeling choices that are not uniquely determined by the data. The assumed star formation histories, metallicity grids, and dust attenuation curves carry priors that can steer the recovered ages and masses. Adopting a constant or gently rising history yields ages of several tens of millions of years, while a strongly bursty history permits younger solutions at the cost of predicting line-dominated colors not supported by the measurements, and this trade-off defines a real degeneracy rather than a simple error bar. The choice of the initial mass function shapes the conversion from ultraviolet luminosity to star formation rate, and from light to mass, and while common forms give similar results over the massive star range deviations in the high mass slope, or an excess of very massive stars would tilt the conversions and shift the reported rates and masses systematically. Nebula contributions add further uncertainty. Nebula continuum can flatten the redwood slope and reduce the inferred dust correction, while emission lines can lift single bands. The current limits argue against extreme equivalent widths, yet moderate lines remain allowed and become an error term that weakens constraints on dust and metallicity. The composition of the interstellar medium and the neutral fraction of the intergalactic medium complicate the blue side of the break. A patchy intergalactic medium can change the depth and sharpness of the break, and introduce sightline variance not captured by smooth models. To avoid bias, the fits allow the blue side to vary within physical bounds, but this freedom broadens the redshift posterior and carries forward into luminosity size in physical units and any rate or mass that scales with distance. Contamination by low-distance interlopers forms a conceptual uncertainty even after extensive checks. Very dusty galaxies with strong lines can in principle mimic colours at this depth. The non-detection in the bluest band to a stringent limit, the smooth red to red ratios, and the absence of a single band excess all disfavour that path, yet the possibility is not reduced to zero, and thus remains a small probability tail that would, if realised, lower the distance and revise all derived quantities. Gravitational lensing is addressed by image plane tests that show no arcs, no mirrored companions, and no strong shear, but a faint foreground satellite or a low luminosity halo very near the line of sight could still provide modest magnification. This would scale intrinsic luminosity and star formation rate downward and shrink the physical size, and the reported values therefore include a margin for weak lensing. Morphology lives near the resolution limit, so the measured size and concentration inherit uncertainties from the point, spread function model, drizzle parameters, and intrapixel response. These enter the conclusion that the source is slightly resolved and nearly round, and while method variations preserve that qualitative picture, the quantitative size and concentration carry large fractional errors that flow into comparisons with theoretical size relations. Selection effects and statistical fluctuations contribute additional uncertainty. Eddington bias can scatter intrinsically fainter sources above the detection threshold and brighten their measured fluxes and completeness, and purity estimates derived from injections are themselves uncertain at low numbers. These biases mostly affect space density inferences rather than the properties of this single object, but they shape any broader statement that places MOM-Z14 among a population. Cosmic variance also limits generalization because a single deep field samples a small region of sky where large-scale structure can skew the local abundance of early galaxies. Time domain effects are a minor but non-zero factor. If the source varied between subsets, averages would hide real changes. The split stacks show stability, yet variability remains an untested dimension on longer baselines. Finally, all uncertainties must be understood as coupled rather than independent. Calibration shifts alter colors that in turn change dust corrections and star formation rates. Template priors that favor certain histories adjust the balance between age and metallicity. Weak lensing scales luminosity and size together, and thereby affect surface brightness arguments. And sightline variations in the intergalactic medium move the break and change the inferred epoch. The analysis addresses these couplings by perturbing inputs jointly repeating the fits across independent reductions and reporting probability ranges rather than single values, but the resulting bounds remain broad. The fair statement is that MOM-Z14 is a robust candidate at extreme distance, with properties measured to first order and with uncertainties that are explicit, propagated and dominated by calibration modelling priors and the faintness of the light at the threshold where the earliest galaxies become visible. The follow-up program for MOM-Z14 is designed to convert a robust photometric candidate into a source with securely measured distance and more precise physical parameters, while keeping instrumentation details only where they link directly to the goals. The first priority is dispersed light that anchors the position of the continuum break and searches for weak lines without relying on a single band excess. A deep prism or low-resolution grating observation with the near-infrared spectrograph would place the discontinuity at a precise observed wavelength and reduce the uncertainty in cosmic epoch. The extraction would follow the imaging catalogue to control overlaps and the background model would be varied within bounds to check stability. Even if no discrete line appears, a measured continuum downturn aligned with the photometric step would narrow the redshift range and propagate a tighter distance into all derived luminosity sizes in physical units and star formation rates. The same spectrum should be examined for subtle crests at positions expected for rest ultraviolet lines, such as carbon-3 and oxygen-3. A non-detection at improved depth would lower the allowed equivalent widths and sharpen the limits on ionized gas conditions assumed in the population fits, while a detection would provide a handle on metallicity and on the hardness of the radiation field. The second priority is imaging that probes redder wavelengths to sample the rest frame optical continuum, because that continuum contains the 400 nanometer break that reacts to the presence of older stars. Deeper imaging with the longer wavelength filters of the near-infrared camera would raise the signal to noise on the red side and test for a gentle curvature that might indicate a maturing stellar population. If the curvature remains absent at higher significance, the bounds on stellar age would tighten toward young to intermediate values. If a small bend appears, the fits would incorporate it and explore whether the allowed age extends upward without violating the observed ultraviolet slope. A complementary step is a search for mid-infrared emission with the mid-infrared instrument at wavelengths, where strong rest optical lines could fall. Even a shallow detection or a strong upper limit would inform the balance between continuum and lines and would reduce the degeneracy among age metallicity and dust that remains when only near-infrared bands are used. The third priority addresses dust directly through far-infrared and submillimeter observations that trace the thermal emission of grains. A pointed observation with the Atacama Large Millimeter Array at frequencies tuned to the expected rest, far infrared peak given the favoured distance, would constrain the dust mass and the fraction of star formation that might be obscured. A non-detection at a depth consistent with the current continuum would set a firm upper limit on dust, supporting the low attenuation inferred from the blue slope. A detection would reveal hidden star formation and revise the conversion from ultraviolet light to total star formation rate. The flux would be combined with the near-infrared measurements to test energy balance and to calibrate attenuation curves at very early times. The fourth priority is a refined lensing assessment that secures the intrinsic luminosity. High-resolution imaging of the foreground field with the same near-infrared camera extended to wider radii would inventory potential deflectors and search for very faint satellites near the line of sight. Spectroscopic redshifts for the nearest blue galaxies obtained with multi-object spectrographs on large ground-based telescopes such as the Very Large Telescope would fix their distances and improve mass estimates used in simple lens models. If the models confirm only weak convergence, the working assumption of negligible magnification would be strengthened. If a modest convergence emerges, the intrinsic luminosity and size would be adjusted downward within the refined bounds. The fifth priority is time stability and reproducibility. Repeating the imaging at a later epoch with similar depth would test for variability that might indicate an active nucleus or a transient. Although variability is not expected for a compact star-forming galaxy on these timescales, a stable flux reinforces the interpretation, while a measurable change would trigger a careful reassessment of population synthesis and ionized gas assumptions. The sixth priority is uniform reanalysis with multiple pipelines. The new data would be processed independently with pipelines that differ in background subtraction drizzle parameters and spectral extraction approaches. Agreement among reductions would reduce the role of method variance in the error budget. The seventh priority is population synthesis updates that are driven by the new constraints rather than by expanded priors. With a tighter distance from spectroscopy, a refined ultraviolet slope from deeper imaging and bounds on dust, from far infrared limits or detections, the age and mass posteriors would narrow. Nebula components would be reweighted according to any detected lines, and the initial mass function dependence would be tested by forward modeling each assumption into observed bands and comparing to the same measurements. The eighth priority is context within the field. The deeper data would revisit the immediate neighborhood selection to test whether the tentative excess of red neighbors persists and whether their colors align with a common epoch. If a small group of high-distance candidates emerges around MOM-Z14, the implications for early clustering would be noted while remaining within descriptive bounds set by the data. Across all priorities, the program maintains a clear chain imaging anchors positions and colors, spectroscopy brackets, the break and searches for faint lines, millimeter observations, test dust and hidden star formation. Foreground spectroscopy secures lensing repetition checks, stability and uniform reductions, and forward modeling convert measurements into bounded physical inferences. Instruments are named only where they provide the necessary link between an observable and a constrained quantity. No step presumes an outcome. Each step narrows a specific uncertainty that propagates through the interpretation. With this program executed, MOM-Z14 would move from a well-vetted photometric record to a source with a measured continuum break tighter limits on lines, direct bounds on dust, and a confirmed lensing environment providing a sharper reference for the closing synthesis. Light from MOM-Z14 crosses most of cosmic history before it reaches the detectors, and yet its imprint is clear in the careful pattern of absence and presence that deep images reveal. A sharp discontinuity separates non-detection in the bluest near-infrared band from coherent detections at longer wavelengths, and a smooth continuum rises beyond the break without prominent crests. The source appears compact and nearly round, only slightly broader than stars, and it occupies a quiet patch of sky, free from bright halos, spikes, or moving artifacts. Test for image processing pitfalls reject persistence, hot pixels, misregistration, and background structure as explanations. Independent reductions recover the same fluxes within the expected noise, and a low-resolution spectrum where available shows a downturn consistent with the photometric step. Under minimal assumptions, this pattern places the galaxy within the first few 100 million years after the beginning of expansion, with a time average formation of new stars that is modest in absolute terms, but significant for so small a system. The colours point to little dust and to metallicities below the solar level as expected for early enrichment, while the lack of a strong hydrogen Lyman-alpha crest aligns with a largely neutral intergalactic medium. No arcs or mirrored pairs appear, no concentrated foreground mass sits nearby, and shapes remain nearly round across bands, all of which disfavour strong lensing and support the working inference that the observed brightness is close to intrinsic. Uncertainties remain and are carried openly. Calibration offsets widen the redshift range template choices, blend age with dust and metallicity. Nebula contributions are limited but not fixed, and weak lensing along the line of sight cannot be excluded. A focused program of deeper dispersed light redder imaging, millimeter limits, or detections, foreground spectroscopy and repeat visits would tighten each bound without overreaching. Within these verified limits, MOM-Z14 extends the frontier of observation by a small, well-measured step, offering a compact, lightly reddened, actively star-forming system at a very early time as a concrete reference for models of assembly and for future measurements that will refine distance composition and the balance between stars, gas, and dust in the young universe.